Oh, lower right.
Oh, slide on the top.
There you go.
So, hello, everybody. My name is Jan Rush. I'm the VP of DVAA, and I'm here sitting in for our president, Harold Goldner, who is busy tonight. So I thought I had to start with a beautiful photo of the James Webb Space Telescope, because since we met last, we had NASA successfully launched and unfurled the James Webb Telescope, and I think we're all really excited to see when we get the first few images in the summer. But tonight we're talking about things a little closer to home. We're going to hear a lot about the Green Bank Observatory from Dr. Lockman. And before we get to all the fantastic science that's happening there, I just wanted to mention something interesting that happens once a year at Green Bank, and that's the Green Bank Star Quest, which is a visual observers star party, not just visual, astrophotography also. It's been canceled the last 2 years, but they are gung-ho this year. And it is a really interesting star party for a couple of features that I'm going to tell you about. It's led by the Central Appalachian Astronomy Club, and it'll be happening the end of June, beginning of July. So here's the observing field where you can set up a telescope and camping gear. It's never crowded. It's really got nice horizons, and it's big. And interestingly, the scientific program is awesome. There are several classrooms as well as an auditorium, and in the classrooms they usually have cover several different topics simultaneously, so you can pick whatever you're interested in. And then they have a lovely air-conditioned auditorium that has great seating, and best of all, they have behind-the-scenes telescope tours where you can actually go up in the large telescope. And another nice feature, if you don't want to camp, they have a bunkhouse. The bunkhouse has hot showers and a little tiny game room refrigerator kind of place where you can hang out if it rains. And also a wonderful scientific program for children. These are the kids launching their homemade rockets. So if you'd like to hear anything about this, I've been there 3 different years and it's been really fun. So I'll take questions when we end the program and we do our informal chat, if anybody's interested in hearing more about the Green Bank Star Quest. So I also wanted to mention that we have now elected officers for 2022. Harold Goldner was re-elected as president. I'm vice president. Louis Berman is treasurer. Mike Tucker is secretary. And we have Barry Johnson and Tracy Trapezzano continuing as members at large. And we have Scott Vanneman as a new member at large. I don't know, Scott, you want to wave or say something? Yeah, there's Hello. Scott, everybody. Also, for those of you who aren't too familiar with the club structure, we also have 3 non-elected board members, and that's Jeremy Carlo as program chair, the welcoming chair, Brian Lee, and the observing chair, Andrew Hitchner. So this is the DVA board, and you are welcome to send any of us your ideas, your comments, anytime. Also, a shout out to Derek Pitts. Many of you, most of you probably know Derek. He's the head of astronomy for the Franklin Institute, and he does a lot of outreach in the city of Philadelphia and the suburbs. And Sky and Telescope did a fantastic article on his work in the February issue, which just hit your mailbox probably. So take a look at it. It's good reading. And finally, since we're talking about Sky and Telescope, I just wanted to mention that the discount buttons for members are now back in operation. Sky and Telescope didn't have their discount link working for a while there because of their change in ownership, but now everything is working. So down at the bottom of the website, if you need to subscribe either to Astronomy Magazine or Sky and Telescope, it's now really easy to get to the discounts for those publications. Okay, now let's go to committee reports. We'll start with Brian.
Okay, we have 5 new members this month. Kind of down from before, but not too bad considering. Anthony Albence, Johanna Plummer, Ted Coates, Cliff Bayak, and Louis Levine. And I didn't see them here tonight, but if anybody, if I called your name, just speak up. That maybe towards the end of the meeting and introduce yourself. That's it for me.
Okay. Louis, how are we doing with renewals?
So we're doing moderately well. I don't remember the exact number, but we have 60 people who have been previous members who have not renewed. That is about average, I have to tell you, at this time of year. But of course, we encourage you to go to the website, log in and renew. And you can, if you don't know how to log in, there's a menu item called support, and you'll get help with real live human support, help you log in and be part of membership. You know, it's your dollars are very important. It helps us make the club more solid to pay for honorariums to speakers to support our mission. So anything you do to help us would be great. And thank you very much.
Okay, thanks, Louis. Roy, you're up with outreach.
I would like to make a plea. We have an event coming up, and the dates are open, but we're talking about beginning of February, first weekend of February, or the second week, or maybe one of each. Have the date on like the 5th, and then the rain date on the 12th, something like that. But I need help. It's for Cub Scouts in Bryn Mawr at the Coopertown Elementary School. Al Lamperti has graciously offered his help, but as far as anybody else, I need hands. I need scopes. I need knowledge. So if you could send me a thing saying that you'll help me, it would be much appreciated. It's our first event of the year. Not even sure exactly when it's going to be. I have to find out how many people I can get, and then we'll go from there.
And Roy, you receive email at outreach@dvaa.org. So
Yes.
That's the easy way to think about it. As a rule for everyone, we have president at DVAA, treasurer, VEEP, observing, there's a whole list of things. And I think they're listed in the newsletter and also on the contact page on the website. So hopefully that makes it easy.
Roy, are you thinking about doing inside things as well as outside things? Is it going to be similar to the
I'm going to have to call the guy and ask him exactly what he's hoping for. Inside things and outside things would probably be good. Like what we do at the Erdenheim Elementary School, that would be similar, something similar to that. I would think would be a good idea. We have inside things, and I'm not even sure. There's supposed to be a room of some sort where we can. It's a somewhat large room, so we can set up a telescope on one end and a little picture of the moon on the other end, and look at if there's bad weather or something like that.
Roy, you can pick a date and then plan on some indoor activities, and if it's clear enough, put the telescopes outside. So telescopes outside might be a plan B if the weather cooperates. If not, we can keep the Cub Scouts happy with some indoor activities.
Right. And this, I'll have to call the guy and ask him. Yeah, so if you can help me and help the club, that would be awesome. And also I'd like a list of people I can contact and for such events as this. And have them as a go-to list, essentially.
If you've participated before in outreach in the last couple of years, you're on the radar screen. So Roy has that list, but I guess it would be good to have a confirmation that people are still interested.
If you're still interested, yeah, I don't want to take you for granted. So just, I'd appreciate it if you could give me a list of, or just send your name in and say, I would love to help.
Okay. Thanks, Roy.
Thank you.
So Al, you have a new initiative you'd like to tell us about, right?
That's right. The DVA has a new initiative. It's called the DVAA Youth Awards. This is the time of year that schools are prepping the students for any science projects and science fairs. And we came up with this idea of a youth award. A number of purposes. One is just to help develop an interest and have young folks present any work they have done, astronomically related. And then hopefully we can get them into the DVAA as a member. One of the prizes would be a free membership, year's membership in the DVAA. Now, how do we go about doing this? Well, you see a flyer that's Jan put up. That's photographs from NASA. One of the Falcon rockets taken off. So what we're doing, what I have done, at least yesterday, I sent this flyer as well as a one-page description of the awards to at least 11 people or organizations in the area. The one-page description is also available on the DVA website. If one just clicks on the button called DVA Youth Awards, you will see that one-page description. And basically it describes the awards. We're looking for students either in junior high or high school as two different categories. If they have an astronomy related science project, to submit it electronically for consideration of an award. The one-page description describes the awards in those two categories. There's monetary award, there's a certificate, a one-year membership in the DVAA, and the ability to perhaps present their project at a DVA meeting. And I also on that publicity flyer, there's a brief description of the categories that would be judged: scientific methods, hypothesis, methodology, data collection, and clarity of presentation. Very general in terms. I just want to give them an idea of what we're looking for. There's a May 1st deadline, so that it comes near the end of the school year and gives us time to look at that. I sent this flyer and what you see in front of you, as well as that little description, to 11 folks, organizations yesterday, and I had a few feedback, some positive feedback so far. The biggest organization is the George Washington Carver Science Fair. That's an all citywide science fair, and astronomy is one of the topics that they encourage students to submit there. So, and Adam Chandri has also given me a lead on the Pennsylvania Junior Academy of Science. I went to their contact page, but the contact page told me to come back later. It's still not quite working yet, but I'll keep trying. The entries will be judged using score sheets. There are a number of them available on the internet, but they're all basically very much the same. We can just pick one and then go from there. What I'm asking is if anybody has any experience with judging science fairs or wish to be a judge in this endeavor, please let me know. Otherwise, I'll be tapping people on the shoulder. And I'm hoping that we will get some applicants. Also, if any of you know of science teachers or have contacts in schools, let me know or let them know, and just have them hit that button on the DVA website and they'll see the information that we need. What are some of the outcomes? Well, one of them is really nothing for the first year, but at least we get our name out there. But if we do get some applicants and do some awards, I think that will word of mouth will spread to other schools, and who knows where we'll go from there. But just as an example of what can happen if one has a high school student has a astronomy related science project, I'll give you as an example, Andrew Hitchener, our observing chair, and see where he is right now, one of the higher paid members of the board on the DVAA. But I remember Andrew in high school doing spectroscopy on stars with his telescope, and he has come a long way with that. So who knows what will happen if we can get some of these kids to submit their astronomy related project. Okay, that's all I have.
Okay, thanks, Al. And if you have any questions for Al, will you be able to hang around a little bit after the meeting, Al?
Okay.
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 All right. Okay, so the astrophotography enthusiasts of DVAA have been very, very active within the last month. And Lou is going to share with us what's been happening.
Okay, so a bunch of us have gotten together and organizing information and techniques, I guess, on how to help you learn astrophotography, or from beginner to advanced. We have, I think right now there's 7 of us. There might be more coming that are experts on specific areas. We can introduce everybody now. If everybody's here, I want to say hello. Let's see, Scott, I see you. You're closest to me on the monitor.
Oh, you didn't want to go first?
Well,
you don't want to introduce yourself?
No,
well,
no,
you do the
I'm
first one.
All right. Well,
all right.
Jane already introduced me. So, all right, I'm Lou Varvarese. I'm the chair for the astrophotography. I rely on all these other people to help me. So I know a little bit about astrophotography, enough to get me into trouble, enough to help beginners and maybe some intermediate people. Anyway, Scott, you can tell people about yourself, and then we can go down the line.
As Jen said, I'm member at large, but obviously my interests are in astrophotography with it. I actually started with wide field, actually, as Roy pointed out, with just a little star tracker, and accidentally pointed it at Orion and went, "Ooh, what's that blurry spot?" And went and bought a bunch of stuff. Not quite that quickly, but just learning. So I think I have a lot of experience in learning the curve of it and the struggles of it. So I would still say that I'm an early learner of it. Say hi to everybody. Say hi to everybody. There you go. So I'm an early learner, but I kind of hope that a lot of it that also comes that helping other people starting out that, I've been doing it for decades with it, so I can still get bridge a gap with people too. So.
All right, I see Tom is next on my screen.
Okay, I've I've dabbled a bit with planetary, lunar, and solar photography mainly. I've just started to get involved with live stacking, it's called, with a program called SharpCap, which I started with using it as merely a way of viewing deep sky objects from my light polluted backyard. But what it allows you to do, it allows you to capture some souvenirs kind of along the way of what you're viewing. And so I'm on the low end of the spectrum of deep sky photography. I do nothing fancy. I'm a point and shoot kind of a guy. I do pretty basic stuff, but I can help people out with SharpCap and a little bit with the lunar and planetary and solar work if they need help or if they're interested.
Thank you very much, Tom. I think Gary, you're next on my screen.
Hi, my background is I've been a member of the club for about 25 years, and I do both visual astronomy observing and also astrophotography. I've been involved in just like landscape photography since I was about 15 years old. So cameras have always been sort of part of what I play around with. So the challenge of astrophotography was something that interested me once I started to get involved in visual astronomy. I started with film cameras with manual tracking through an eyepiece, and then when digital cameras came about, it really opened it up to a whole other level of astrophotography, made things much easier. So I started with an unmodified DSLR camera and webcams to do planetary. So unmodified DSLR for deep sky stuff and webcams for doing planets and things like that. And I'm anxious to learn more and anxious to help people as we all learn in this activity and in this hobby. I used Photoshop for stacking back then because that was really the only tool available. It was all done manually, and now with the software available, it just makes things much easier. But also the challenges, you keep raising the bar as you go. So anyway, we're here to help and learn as the people that are involved in it, the club members, learn.
Thank you, Gary. How about Bob Triple-Clock? You want to introduce yourself?
Yeah.
Bob, you're muted.
Yeah, I do astrophotography with a cooled camera, monochrome camera. I've collected a lot of data, but I haven't processed very much. So that's where I'm hoping to learn in the future. So.
All right, thanks, Bob. All right, we have a couple other people, but they're not here.
But Joe Lamb, I think I saw him.
Is he Joe?
I'm here.
Joe, I'm so sorry.
That's okay.
Oh, because your name is not on there. That's right. All right, Joe, take it away.
I've kind of been doing it, astrophotography for a long time. I've done some planetary and lunar and deep sky, but I've really liked probably the most wide field photography using a tracker, and I've collected several trackers over the years, and I really like that, and I think it's a great way for people to get into astrophotography. Although they're simple devices, they can produce some wonderful results, and I'd like to share that particularly a little bit with folks, and even just demonstrate some of the equipment that I have, because I really think that's a great way to get into it, and I think as I mentioned, I think the results are really good with that. So I'm really excited about this little collaboration that we have, and hopefully everyone, including us, will benefit from it. So
thank you, Joe. Did I miss anyone? Okay, so Frank also said he might help, but right now he's taking a break from too much. I guess his eyes are strained from looking at all those stars. but he might pop in on occasion and give us some input. And I think Mark Ferrari also mentioned that he would like to help assist. So let me give you a quick look at what we've done so far on how you guys can access the help that we want to offer. Let me share my screen. All right. Can you see the website? So you guys can see the screen?
Yes.
All right. So this is a new page that we just created. It's a landing page or a page to start off on if you are interested in astrophotography. There's some useful links here. Here is, our mug shots. You want to go through here and look if you want to see what our specialties are. I mean, this is not completely filled out. Well, this is still a work in progress. Now, this is what the public sees when they log into our website. So the public has access to all, this information. But when you log in, we should have more resources available. I guess Scott changed the page without telling me. Okay.
No, you didn't log in. Lou, you're not logged in.
Oh, I'm not logged in. Okay. I blamed you anyways. There we go.
Fine. There we go.
Come on.
You're on it. You're on it now.
There we go. Here we go. So
I didn't take the page on you, but
well, at any rate, this page will constantly be evolving. But this eventually will have this a little more organized. We're just getting the information all in one place. So if you have an image you want critiqued, you want to show off, if you have a general question that you want to ask any one of us, the best place to do it is if you click on the link here and just go directly to the astrophotography forum on our website. You'd start a new thread, and when you post it here, the moderators will all get alerted and somebody will answer your question. What you could do is you go in the preferences in here and make sure you put your email address in here, and you can select if you want to have a notification when someone posts something new on the forum. So if you want to participate, it's a good idea to set up those settings so you get alerted. The one thing that we're doing now is an imaging challenge. So we're halfway into the winter season now, and there's not that many clear nights left. Maybe 2 more new moon opportunities. I don't even know if we're going to have that many with the clouds, but these are the targets I have suggested. Now, Carrie came up with another idea, and I think we're going to implement that idea on target selection for the next time around. But if anybody wants to participate, whatever picture you have, just reply to the forum with your image. And that way, everybody can, with their images interested, can reply, and we can select a winner from there. And the winner will have their image posted in the newsletter. So if the winter challenge will be over at the spring equinox in March. So, presumably it would be posted in the April newsletter. All right. Does anybody have any questions? No? Okay. I'll give it back to you, Jan.
Thanks, Lou. I'm really impressed with all the work that your team's done in a very short period of time. It's been great. Okay, I think last up is Andrew with the observing report.
All right, thanks, Jan. Let me share my screen here. All right. My name is Andrew Hitchner. I'm the observing chair, as mentioned before. As Al mentioned, I am a highly paid member. I am a chair of a committee of 1, so I pay my own bills. So, for those of you who are new to the club, I do these observing reports in every single meeting, and then I am also the one who organizes the star parties and makes the calls. If you've ever called the Star Party hotline. That's my beautiful voice that you're hearing, making the go, no-go decision. As far as Star Parties to go, I did want to mention that still ironing out the dates. We're playing around with having a potential backup date for the Star Parties, maybe the Friday before that scheduled Saturday, to maybe open it up, because a few times last year, we could have had a Star Party if it was just a day before or after the actual date. So talking to Valley Forge about what that is, although I don't see them having a problem with it. And our first Star Party of the year will be March 12th at 6 p.m. So looking forward to that. Do whatever you need to do do your no cloudy dance or whatever. So, but without further ado, this is the observing report for January 2022. And it's been a pretty hot topic lately. So I wanted to talk about asteroids. And, you know, usually here I have like a nice picture that I found on the internet or whatever. There's not a lot of photos of asteroids, to be honest. There's a lot of artist renditions. So I thought, well, why not include this great picture that Lou actually just took of asteroid 7036. You can see the name down there. I'm not going to try and pronounce it. And then it's moving through IC 443. So great job, Lou. It's a really interesting photo. And this is how you would kind of actually go observing asteroids too. You know, you would look up where the asteroid is using a planetarium software, and then you would look at that area and try and find the star that isn't marked in your catalog. So great job, Lou. So first, let's go, what is an actual asteroid? So they're technically defined as minor planets of the inner solar system. And I say inner solar system because previously they were just minor planets. And then, you know, asteroids are one thing and the comets were another. Although through further study, they found that a lot of the asteroids or so in the Kuiper Belt actually had more characteristics of a comet. They just weren't close enough to the sun to have that nice tail. So they decided that asteroids, they being the International Astronomy Union, decided that asteroids would only be in the inner solar system. Those in the asteroid belt, and also co-orbital with Jupiter, because Jupiter is really big and it picks up a lot of stuff. And those are called the Jupiter Trojans. They kind of follow behind it. Now, asteroids are composed of minerals and rocks, unlike comets, which are usually dust and ice. And they are defined to have a diameter greater than 1 meter. Anything less than 1 meter is a meteorite. Now, there's millions of asteroids out there, and they vary very greatly. The largest series, which is about 1,000 kilometers wide, and then they, of course, have 1 meter there. And then you can break them up even finer based on the spectrum of the asteroids. So there's C-type, M-type, and S-type. The M-types are like really high in metals. The S-types are really, they have some silicon in them. But to us, you know, we think more along the lines of their size. I think there's an open mic out there. Somebody can, everyone can check and make sure they're muted. So relatively, they're pretty small compared to like planets and such, which actually makes them really hard to directly observe. And remember, these are just rocks and minerals and stuff, so they have pretty low reflectivity too. So that makes it pretty difficult to observe them. And Stephen Hawking, in his book, Brief Answers to Big Questions, called asteroids the greatest threat to our planet, which is kind of going to be a theme throughout this presentation. So if we look here, this is kind of a diagram of the solar system, of course, with the main asteroid belt here, and then, of course, these Trojan asteroids that Jupiter has collected as it orbits around the sun. And then anything past the orbit of Jupiter would be considered another kind of object, like a Kuiper Belt object or a comet, maybe, or so. So recently in the news, I think it was last Tuesday, there was asteroid 7482 or so that passed pretty close to the Earth. It was 1 kilometer wide, and it passed the Earth, let's see, at about 5 lunar distances or so. So that is a near-Earth object. So near-Earth objects are small solar system bodies that approach close to the Earth. And they're mostly comprised of comets and asteroids with I think about 90% or so being asteroids. So sometimes you'll hear them referred to as NEAs, near-Earth asteroids. But there's a little ambiguity in that definition. So what do you mean by close? So close is if the perihelion, or the closest approach of the object, is closer than 1.3 AU to the sun. And then these NEOs are potentially hazardous if their orbit crosses the Earth's orbit, and if they're larger than 140 meters. So the NEO that passed close to the Earth on Tuesday is 1 kilometer wide. So it definitely fits that potentially hazardous category. Now, there's about 27,000 known NEOs, and there's some pretty big ones out there. One of note that I found while researched is, I have the date wrong there, but it's a 0.9 kilometer asteroid, 2001 WN, will approach the Earth within 0.65 lunar distances in 2028, actually, not 2021. 0.65 lunar distances is actually really close. So hopefully they have a low sigma on the observations of that asteroid's orbit. So here's a diagram. These are all of the tracked, known, potentially hazardous asteroids within the solar system. And I don't know about you, but I get a little anxiety looking at this graph, because there are definitely a lot of them. Here is Earth's orbit, and here all of these asteroids and a few comets, their orbits pass within the Earth's orbit, and they get pretty close to the Earth. Now, luckily, we are doing things about this. So there's a international project out there called Project Space Guard. It was inspired by Rendezvous with Rama by Arthur C. Clarke. And in that, in the book, they describe a sort of, monitoring system based on an asteroid collision. Now, in 1992, the US Congress mandated NASA to catalog NEOs greater than 1 kilometer in diameter. And this was fulfilled back in 2011. And since then, in 1995, the IAU held a working group to establish an international collaboration, because the more telescopes we have looking at these things, the more likely we're able to find them. And you need repeated observations of the same object in order to determine the orbit of the object, and usually over a long period of time. And this has been known to be the Space Guard Foundation. And like I said, this is an international collaboration. So there's observations being made by telescopes, ground-based telescopes all over the world. Now, as I mentioned before, because of the unique nature of asteroids, they're kind of hard to find. And you need a pretty big telescope, pretty sensitive telescope, in order to track these objects. And they're not done by people, usually. It's done by a computer with a telescope that is manually surveying the sky and finding these asteroids. And it is done by things like changes in brightness and object moving and stuff, which is one of the downsides of, or one of the potential downsides that people are arguing with these very large satellite constellations that you hear about, definitely with like SpaceX and Planet Labs and all. There's a lot of upsides to these things, but there's also a lot of downsides, whereas they could create a lot of false alarms with these NEO observing systems, and that could be pretty catastrophic. Now, you could argue, well, there's nothing that we could have done, even if we did see it, but I like to know about these kinds of things. So just something of note there. But maybe there is something we could do. We see this hazardous asteroid coming at the Earth. I mean, come on, we're pretty technologically advanced. What can we do? Well, NASA has thought of this, and they have the double asteroid redirection test, and it's called DART. And the goal is the spacecraft is 500 kilograms, and it will be traveling about 6.6 kilometers a second. That's about 4 miles a second. And it will impact an asteroid. You can see that the asteroid's named is Dimorphos. It's actually a double asteroid. But it will crash into this asteroid deliberately, and it will change the velocity of the asteroid by about 0.4 millimeters a second. Now, you might think that's not a lot, right? But the goal is that this should, over a really long period of time, change the trajectory of the asteroid and hopefully change it in a way that it would then be not on a collision course with Earth. Now, this asteroid, though, Dimorphos, is not, this is a test, right? It's not going to hit Earth. They just want to see if we do impact an asteroid, can we have any say over where that asteroid ends up going? So this launched back in 24th November 2021 to little fanfare, of course, with the James Webb Telescope going up about the same time. And it is scheduled to impact between 26th September or the 2nd of October, depending on where the asteroid actually is. So be on the lookout in the news. It's pretty fantastic that we're actually able to do this. And here's the picture of the satellite. To be honest, 500 kilograms, it's actually a pretty small satellite. And they probably designed it that way and able to get it up there pretty fast, you know, in case we don't have a lot of warning before we find these asteroids. And I like this artist rendition because you can see the little camera on here. That is the only, besides the power and like the RF transmitter, the camera's the only like instrument, if you say, on there, because that's just going to be tracking the asteroid until impact. So pretty cool stuff. You know, there's a lot of things out there that we're not aware of. We're trying to track and find more things. So I just want to leave you with this heartwarming quote by the B612 Foundation, which is a nonprofit space foundation where it's 100% certain we'll be hit by a devastating asteroid, but we're not 100% sure when it will be. So with that, I'll say thanks and I'll turn it back over to Jan.
Okay, well, thank you very much, I think, Andrew. I think we're ready now for our featured speaker. So I'll turn it over to Jeremy to introduce Dr. Luckman.
All right. Thanks, Jan, very much. Great meeting so far. Heard a lot of really nice stuff going on in the club. So I want to give a special welcome to all the folks joining us on YouTube. We actually have 24 people joining us on that side, to almost as many as on Zoom. So we're getting a lot of exposure there. So people watching us live and also the people who will be watching us in the future. So just a reminder, if you are not the speaker, please mute during the presentation to keep the noise level down a little bit. So it's my pleasure this evening to introduce Dr. Jay Lockman. Jay is the principal scientist at the Green Bank Telescope, located at the Green Bank Observatory in West Virginia, which Jan told us a little about at the beginning, and Jay showed us a picture just as we were coming online. So Jay actually did his undergraduate work right down the road at Drexel University. He did his PhD at UMass Amherst, and his research is in the structure and evolution of the Milky Way and other galaxies, and a particular interest in the mapping of hydrogen, which is one of the great things that can be done with radio astronomy. So tonight, Jay is going to give us kind of an interesting talk. It's going to be on particularly radio astronomy, and are the biggest discoveries due to serendipity, essentially lucking into them, or is it the result of sweat? So I guess it's the old perspiration versus inspiration, as Edison pointed out. So please join me in welcoming Jay Lockman.
Thanks. I'll start sharing the screen here.
All right.
And yeah, first of all, I want to thank you very much for inviting me. And I submitted 3 possible talks, and I'm really pleased that you chose this one, because it's forced me to look into this topic, which I've been kind of playing with for the last year or so, look into it in more detail. And I think I'm going to continue on this track because it's a fascinating insight into the way science works in addition to being some very fun stories of a historical nature, well, continuing up to the present. But serendipity or sweat, okay? So there's serendipity on the left. I'll define these terms in a minute, but they kind of bolt from the blue, and we all know what sweat is. Serendipity, the definition is the faculty of making fortunate discoveries by accident. And this word was coined, let me see if I can get rid of, there we go. This word was coined by Horace Walpole when he wrote about something else, this discovery indeed is almost of the kind which I call serendipity, a very expressive word. Walpole got it from a silly fairy tale called The Three Princes of Serendip. As their highnesses traveled, they were always making discoveries by accidents and sagacity of things which they were not in quest of. And there's a little illustration to the left of our princes of serendipity. I'm having trouble advancing the slides. I have a couple of possible ways out of this. In fact, this is completely frozen now.
Are you sure the PowerPoint is active?
It is. This is actually Keynote.
Okay.
But it has never done this to me before. But I also clicked something in the upper left in order to hide my own picture. And so let's see if that does anything. No. Oh, okay. I somehow seem to have advanced it now. Okay, on the topic of serendipity, I found this amazing publication, the Princeton Alumni Weekly, from May 14th, 2008. And I knew about this discovery and I was hunting for it because it seemed to me a perfect definition of serendipity. Anyway, the Alumni Weekly reports Supernova Serendipity. And the story is that Alicia Soderberg, a postdoctoral researcher, looking with the Swift satellite at a galaxy, saw something extremely bright on the screen of her computer. And she realized that she was seeing a supernova in the process of happening, something very rare and unexpected. And she describes the experience as being in the right place at the right time and with the right telescope and says, I won the lottery. Now, this is serendipity. I should point out, though, that her former advisor, Bob Kirshner from Harvard, stressed that luck was only part of Soderberg's finding. You know, if you're active and you're energetic, it helps a lot because you manufacture your own luck in a way. So Kirshner is suggesting that we may have a little sweat leaking into the world of serendipity here. Sweat, definition, the one we care about, is to work long and hard. And there's plenty of examples that one could find on the internet of sweat if you're interested in that sort of thing. And in this, it's really, truly amazing because of this issue of the Princeton Alumni Weekly, of which I have no association with, had only 2 articles. One was the serendipitous discovery of a supernova, and the other was this little short article on the bottom about a Princeton student completing 1,000 push-ups in 20 minutes and 50 seconds, setting a new world record. Now, this activity is sweat, if anything is sweat. And the fact that both of these were in the same newsletter, well, that's got to be serendipity, right? So I'm going to talk about some discoveries in astronomy and really strictly radio astronomy because that's what I know the most about. That's the sea that I swim in. And the more I got into this, the more I was discovering that there was a world of discovery that could be talked about. And I don't know whether I'm gonna have time to go all the ones listed here in white: extraterrestrial radio waves, radio bursts from Jupiter and the sun, the Big Bang, pulsars. And I just listed some at the bottom in color: quasars, Sagittarius star, the black hole at the center of the Milky Way, the binary pulsar. That one could go on and on and on, but I'm not going to talk about those tonight. I don't really have the time. But let's start at the very beginning with Carl Jansky in Bell Telephone Labs. He was, I'm going to try to, if I can, yeah, okay. Now I can see my whole screen. Carl Jansky was a young engineer who was hired in the early 1930s by Bell Telephone Labs in Holmdel, New Jersey. And he was given the task of finding out sources of radio interference that might affect the then new field of transatlantic radio communications. Radio communications were burgeoning, and the whole question was, what was going to be the limit to the amount of information and data that you could transmit at long distances? So he built this device. And those of you who've been to Green Bank, we have a copy of it, not the original, but a copy of this device in the front field. It operated at 20.5 megahertz. And he scanned the sky. It went around every few minutes it would go around once, and he was looking a little bit above the horizon. And what he noticed was that the radio signals he detected could be divided into a few categories. One was nearby thunderstorms, they were easy. There was also another kind of emission that was sporadic, and he figured that that had to be from distant thunderstorms. But there was also a more or less constant emission shown here with the arrows on his chart recording. And it moved through the year, rising and setting at different times. Well, sure enough, what's happening? Okay, he had discovered radio waves that he traced to the center of the Milky Way. And this was a from the New York Times, mysterious static, direction is unchanging, and note on the bottom right, no evidence of interstellar signaling. You know, we take for granted right now that the solar system, if not devoid of life except on Earth, at least the life is pretty well hidden. But in the 1920s and 30s, that was not at all the prevailing view. So the thought that he could be seeing something from extraterrestrial civilizations was certainly a possibility. And he discovered radio signals from the Milky Way and started the field of radio astronomy. So I'm going to ask this question over and over in this talk. Was this serendipity or was this sweat? And we'll come back to the Jansky at the very end. Now, there was a problem with Jansky's discovery and a reason why it lay fallow for perhaps 15 years. For one thing, he was an electrical engineer and he really didn't get a chance to follow up his discovery. And it was not really something that astronomers could comprehend. They couldn't get their hands around it. And here's a big reason why. The graph I show here shows the way that any object emits radiation because of its heat. And these are logarithmic curves, and you can see frequency and wavelength down there. And if you get something that's as hot as a star, 4,000, 7,000 kelvins, you see that it emits in the infrared and the visible and the ultraviolet. Something which is only 300 kelvins emits in the infrared and so on. But notice the nature of these curves. No matter what the object is, the intensity drops off as you go to longer wavelengths, to lower frequencies. So Jansky's point was kind of up here in the upper left. So what the heck was this stuff that was emitting radio waves? And that was a question which took a long time to resolve. Along comes one of the most interesting people I've ever been privileged to meet, Groat Reaber. He was right out of college in the mid-1930s. He was working as an electrical engineer, living at the family home with his mother. His father had died. And he decided to follow up on Jansky's discovery. And he built this in the yard next to his house. It was the first radio dish, and he got just about everything right. He built it out of money from his own pocket, out of his own design. It was almost 32 feet across. He built it, scaled the size to pieces he could buy at the hardware store, and so on. Not only built all the mechanical stuff and designed it, but also had to build all the electronics. There wasn't just things that you could buy. And I want to emphasize where he was doing this. I'm blowing up on the next picture, the lower right-hand corner of this picture. You see the picket fence back there? It was in a yard in a suburb. And naturally, it attracted some attention. This is a little local newspaper article. What is it? All Wheaton ponders the purpose of three-story mystery contraption erected by Peter Rieber. They even got his name wrong, but it was a contraption. And so what he did was he knew enough physics that he knew that if Jansky saw something down at 0.02 gigahertz, the intensity should rise with frequency, just as all these curves rise with frequency. So he started his work at 3.3 gigahertz, which was a very high frequency to be working at the time. He saw nothing, just nothing. This is a picture of some of his equipment here. We've got a lot of it at Green Bank. He gave it to us. He was spending summers at Green Bank late in his life. And there's a picture again of his dish on the left with the tower that he used to access his receivers. Well, he got nothing, but he wasn't discouraged. He rebuilt all of his electronics to work at a lower frequency and went back, and this time down at 900 megahertz, 0.9 gigahertz. Still nothing. And Rieber later said that that might have been discouraging to some people, but to him, it just whetted his appetite. It made him more determined than ever to succeed. Here's a photograph of him up there at the focal point with his electronics. So he rebuilt his electronics, built new receivers to work now at 160 megahertz, 0.16 gigahertz, and there it is on the left. He got a detection. And he proceeded then to observe and just try to map the sky. This is a chart recording of his, and all of that fuzz that you see on there is interference from passing motor cars. There's spark plugs, coils, ignition systems, and everything. So the very first deliberate radio astronomer got knocked out by interference, a problem that has remained with us to this day. He ended up only working at night when there was less interference. But the broad curves that you see there, that's radio emission from the Milky Way. And here's really the confounding thing. If you draw a line between Jansky's data and Rieber's data, it goes in the exact opposite direction of thermal radio emission. What in the world was this stuff that was producing radio waves? Well, Rieber wrote this paper, imaginatively titled Cosmic Static. It was published in 1944, and he mapped the Milky Way, discovered some sources and so on. Was this serendipity or was this sweat? I'm going to move now to the Southern Hemisphere to another pioneer in radio astronomy, Ruby Paine Scott, in Sydney, Australia in 1942. Paine Scott had her degree in physics from Sydney University. She was considered the most brilliant mathematical physicist of her generation. And she was recruited during World War II to work on the Australian radar project. Australia was very much in fear of invasion by the Japanese, and so they set up a station outside Sydney. Actually, I think I've got a picture. Yes, there's their station outside Sydney. In the back, these are on the cliffs to the south of Sydney. In the back is the harbor, and they started developing radar there. Well, an amazing thing was when the war ended, this very talented group who had a lot of experience in radar and radio techniques were told by their supervisor to apply it to a civilian use. And they went into radio astronomy. And so they set up and very quickly started discovering things about the sun, that it had these very interesting solar radio bursts. And here are the top two plots show the same frequency, but two polarizations. And then the bottom shows this different frequency. The fact that the bursts were occurring at different times at different frequencies at different times indicated that whatever was making them had a spatial structure, and that it would go off at one part of the flare, as it turns out, and then they would see later deeper into the flare radiation at another frequency. And the fact that the signals were not the same at the two polarizations indicated that it was really not thermal radio emission, but somehow it has a preferred direction of polarization. Again, serendipity or sweat. Let me pause for a moment and talk about these three pioneers of radio astronomy, Carl Jansky, Groat Reaber, and Ruby Paine Scott. Jansky died young. He was never very healthy. In fact, they took a little string pulling to actually get him to pass the Bell Labs physical. He died in his early 40s, in the early 1950s. He never saw what became of his discovery. Certainly, had he lived another decade, he would have gotten the Nobel Prize for launching this amazing new field. Rieber, in contrast, lived until his 90s, cranky and active as ever, always off on some new direction. If he saw the scientific world moving to the right, he was going to move somewhere in the different direction, maybe to the left or more likely straight up. Extremely interesting guy, but he got to see the rewards of his research become widely known. Paine Scott had a very different ending to her career because she had done something previously to her work on radio astronomy, which was so out of bounds that when it was discovered she lost her job, her pension was taken away, and she really was reduced to taking temporary employment. And what she had done, she was a civil servant working for the Australian government. What she had done was committed the unpardonable offense of getting married. And in those days, the rule was that any woman that got married forfeited her position immediately. And so she worked on temporary positions for a few years and then left totally in order to raise a family because there was no provision at all for family leave. Australia's come around and they now offer a Ruby Paine Scott fellowship to women to allow them to take family leave. And interestingly, a few years ago, the New York Times discovered that its obituaries were dominated by dead white guys. So they started trying to make it up by having obituaries of people that really should have been in the Times. And there's Ruby Paine Scott, her obituary, explaining what she did for radio astronomy. We're going to move now, still stay in World War II, but move to the Netherlands. Jan Oort was one of the dominant astronomers of the 20th century. He discovered the Oort cloud, he discovered the rotation of the Milky Way, and on and on and on. But his situation in early 1940s was very different than these other people because the, oops, come on. What do I have to do to make? All right, I will try to get this to change. Oh, there we go. Is because the Netherlands was invaded by Nazi Germany. They started discriminating against Jewish faculty at the University of Leiden, where Oort was, and he was very vocal in his protests. The faculty closed the university and Oort went into hiding. I think he was not searched for very hard, but it was very important that he not be seen publicly because he could be caught and taken away. The story of how he met a young man, Hank van der Hulst, is truly remarkable and is too long to go into here. But van der Hulst was also in hiding because he was a young man in his mid-20s, and had he been rounded up, he would have been sent to a slave labor camp. But he was a graduate student in astronomy. And even though the university was closed, Oort managed, he was living in the country, he managed to bicycle into Leiden now and again with manuscripts hidden in the pump of the tire pump of his bicycle, and organize occasional meetings to discuss recent advances in astronomy. And he ran into van der Hulst and suggested that van der Hulst look for some way that an element like hydrogen would give off a distinctive radio signal. So they had a colloquium in April 1944, and this is a reproduction, a reenactment of the colloquium. And I often wondered, why didn't anybody take a picture at the time? And I suddenly realized that if that picture had fallen into the wrong hands, everybody would have been in big trouble. And so I like to think of van der Hulst working under these amazing conditions of Nazi-occupied the Netherlands and Oort to make this fundamental discovery, the prediction there'd be radio emission from hydrogen, and the theory to back it up. And every time I'm feeling a little grumpy about getting out of bed in the morning and doing the work I got to do, I think, well, I could have been in the wartime Netherlands trying to get something done. The prediction was one thing, the discovery is something else. And there was a race on. And the race was won by Ewan and Purcell at Harvard. Doc Ewan was finishing up a PhD, and his advisor, Ed Purcell, suggested that he go to look for this elusive 21 centimeter emission from hydrogen. They decided it would be undetectable. And so Purcell told Ewan, and we're seeing Ewan sitting there by this horn, your thesis is going to be about something you didn't detect. It's got to be 10 times better than if you actually detected it. And so they built this horn and stuck it out of the second floor lab. I believe it's second or third floor lab at Harvard University. And Ewan tells the story about coming back from lunch one day to work on this. And there below the horn was the junior physics faculty at Harvard trying to throw snowballs into it. And his comment was, the physics faculty can smell a failed thesis a mile away. But it wasn't a failure. And in fact, they did detect the radio emission. They wired the news to Oort in the Netherlands, and Oort very quickly, using this dish, Oort would have found it first, but he had had a fire in his lab. And this was a abandoned German radar dish on the coast of the Netherlands. Oort quickly confirmed the discovery, which was then confirmed also in Australia by a group at Sydney. Serendipity or sweat. This was Ewan. We have Ewan's horn at Green Bank. There's Ewan at the 50th anniversary, standing next to it, and Van der Hulst and Oort in 1964. A lot of sweat went into this thing. I don't think this is a category that anyone would say was serendipitous. Although I must say the meeting between Oort and Van der Hulst was an amazing example of serendipity. A little bit later, we're jumping 5 years now or so, to a field outside of Washington, DC, in Potomac, Maryland, kind of on the Potomac River, where Burke and Franklin set up this array of dipoles. And they had 2 rows, each 1,000 feet long, strung up with these dipoles. And they were looking at 22 megahertz, basically Jansky's frequency. And they were looking for evidence of radio emission from individual objects. And they found that, but they also found something else. And here's the chart recording of theirs. And I'm pointing that this is the Crab Nebula. So they've lined this Crab Nebula up, okay? And they saw something else that was coming at different times than the Crab Nebula. And first they thought it might have been a farmer returning home at night with his tractor, but it didn't seem right for that. And they have a little funny article, I've highlighted it yellow. We examined this little thing for a while, wondering what it was. And it turned out to be radio bursts from the planet Jupiter. And here is this wonderful headline from the New York Times about it seems so improbable, right? Discoveries about Jupiter coming out of Maryland. This is a really funny article. And parts of it highlight the fact that it was detected with a radio, quote, telescope, unquote, near Seneca, Maryland. A radio telescope is no telescope at all. It's a huge, highly sensitive radio receiver. And let me just point out that at this time, when people using technology developed in World War II started scanning the sky groups all over the world, there was a huge kerfuffle. The idea that you could have radio astronomy, an adjective in front of astronomy. A lot of people, classic astronomers, just rejected. They said, it's not astronomy. It's not astronomy. And now, as Woody Sullivan pointed out, because of the radio observations, it forced the adjective optical in front of what was traditionally astronomy. We now know that these bursts are coming by some interaction between material expelled from Io and the magnetic field of Jupiter itself. There's a lot of puzzles about this still. In fact, this is a radio image of the planet Jupiter, and the image in the center is the thermal emission from Jupiter just because it has some heat. It gives off radio waves. But we see here the radiation belts of Jupiter that are picking up charged particles from the sun in the magnetic fields. And that, in fact, was the common thing of the work of Jansky, Rieber, Paine, Scott, Burke, and Franklin, that what they saw was not thermal emission, although it really took until the 1950s to understand what it was. Instead, it was relativistic particles, electrons moving near the speed of light in a magnetic field. And this allowed us to probe conditions in the universe that just did not give off light in any significant way. Around the time of Burke and Franklin, the National Radio Astronomy Observatory was founded in Green Bank, West Virginia, and around it, shown here in the yellow crosshatches, was the National Radio Quiet Zone. Within this area of 13,000 square miles, new transmitters are regulated to the benefit of radio astronomy. It's a unique place in North America, and there will never be another like it. Runs right up through the middle of the University of Virginia grounds. At Green Bank, the 300-foot telescope was completed in 1962. And that gave US astronomers, for the first time, enough angular resolution to be able to look at individual galaxies and study their hydrogen. And here's a map made by Mort Roberts. When I was at Drexel, I was a co-op student, and I got sent to Charlottesville, Virginia to work with Mort Roberts. I apprenticed to Mort. As a matter of fact, there's a reasonable chance that I drew this contour map from radio data. But what we're showing here in contours is hydrogen, and there's an optical photograph of our famous M51, the Whirlpool galaxy. You can see that the hydrogen goes way out beyond the galaxy image. In fact, not only that, because of the Doppler shift, we can measure the velocity of the hydrogen. And here's an image of the Andromeda galaxy and the kind of problem that radio astronomers very quickly ran into. We know from Kepler's law, which is in the upper left, that the velocity of an object needed to be maintained in rotation around another object is related to the gravitational constant g, the mass enclosed in the radius r. And so here we got a figure of Andromeda, and what we expect the rotational velocity to look like is this. It rises, it rises, it rises as you get more mass enclosed. But then at some point you run out of mass, it turns over and follows this line here. Now with hydrogen measurements, people are able to probe way out beyond the visible image of the galaxy. And so this was what was calculated, but in fact, this was what was measured. A rotation curve that didn't decrease even when you were way outside the galaxy. This is not a small effect. It is a major, major discrepancy. And from this was a key bit of evidence that galaxies are dominated by dark matter. This is a great example of a galaxy shown here in the center, its stars, and the amazing hydrogen cloud that surrounds it. There's no way that that hydrogen cloud could be bound to that galaxy without dark matter. Here's three pioneers of the dark matter. I was privileged to work with them all. There's Mort, my kind of mentor, and I did a postdoc with Kent and Vera, and they were working in the optical, and Mort was working in the radio, and the three of them actually wrote a number of papers together. Discovery of dark matter, serendipity or sweat. Well, they certainly were not looking for dark matter when they started this work. Pulsars. We're jumping to Cambridge, England now, in a field there. Jocelyn Bell, at the time, now Jocelyn Bell Burnell, was a graduate student at the University of Cambridge, and her advisor, Anthony Hewish, was building this amazing array covering 4.5 acres that was working at 80 megahertz. The goal of this was to look for radio sources that twinkled. Now, as you know, stars twinkle because they have a tiny angular size, whereas things like planets and asteroids do not twinkle. Well, the twinkles from one part cancel the twinkles from another part. So you see more or less steady emission from things like planets and asteroids. So they were out to find quasars, these very strange stellar-like radio sources. And so they decided to look for things that twinkled. So they set up this very sensitive array, and Jocelyn Bell Burnell and the rest of the graduate students were busy hammering things, moving wires. I've got some slides from a talk she gave. Typical working conditions for a PhD student, putting 1,000 wooden posts in, stringing 100 miles of wire and cable. She said by the end of one of the summers there, the graduate students could swing a 20-pound hammer. And let me just digress for a second to say, those of you that know the story of John Henry, the steel driving man, he only swung a 9-pound hammer. So those were some tough graduate students at Cambridge. I asked Jocelyn about this the one time I met her, and she said, well, we didn't swing it all the time. So she's sticking with the 20 pounds. Anyway, this then produced chart recording, no computers, just chart recording that had to be analyzed. 100 feet a day, 3.3 miles total. And she went over it and found an interesting scruff. Occasionally, a 1/4 inch of the 400 feet showed an unusual signal, and it could be distinguished. She could distinguish it from interference. It didn't look like interference to her eye. This is it over here on the left, and this is interference. They finally confirmed that it was real, got some images from a pointed telescope that just tracked it at a different frequency and saw this train of pulses. And this was the discovery of pulsars. Very important in astronomy, very important in modern astrophysics. Was this serendipity or was this sweat? I have just one slide here about a more recent discovery by Dunk Lorimer of West Virginia University. Again, looking through a sky survey, this time from the Parkes radio telescope, hundreds of hours. And in this hundreds of hours of data, he discovered this blip that is milliseconds wide. And the curve here shows that it did not originate on Earth, that in fact it had to travel through a lot of interstellar space. I don't have time to go into that right now, but I will never forget when Dunk gave a little informal talk at Green Bank about this. There was only one pulse. They went back and looked for 100 hours and couldn't find it any repeating. But this was the first of what we now call fast radio bursts. And there was a lot of skepticism about the reality of this pulse. One reason there was a lot of skepticism is that telescopes like the Parkes radio telescope that discovered this have a problem with scattered light. When you have legs like this in the way, you could have a signal coming off from the right, say a microwave oven that wasn't shielded, that bounced bing, 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 and got up into the receiver. But Dunk convinced himself that wasn't the case, and we now know that fast radio bursts were discovered by hard work of looking at a lot of data. Maybe serendipity. Let me just digress to how a parabolic reflector works, and this is probably no news to all of you, but it's important to the next part of the story. A parabola, shown here in red, has the nice property that an incoming plane wave gets reflected to a single focal point. Now, if your focal point is right here in the middle, like it is with normal radio telescopes with Parkes, and here's the 140 foot from Green Bank, you see you have a problem of blockage and potentially scattering. But it's also true that any one segment of the parabola will reflect that same plane wave to the same focus. And so if you just decide to build this part of your parabola with the focus off to the side, you have the Green Bank telescope. You can look at another part of the parabola shown here with the blue lines, where you're using part of the parabola that's at the same height above the vertex point as your focal point. You could build that part of the parabola. And that's what Bell Labs did in the 1960s, called a horn reflector antenna. And you see, there's the part of the parabola. They've covered the path with metal, and it goes into a focal point, which is in this building at the right. These used to be all over the country as microwave transmission lines. And here's the same design you see up on top of a building. Now most of them have been replaced by fiber. This was built to communicate with a large balloon that was going to be launched around the United States, but that's a different story. In fact, these two scientists, Penzias and Wilson, Penzias on the right, Wilson on the left, were trying to use the horn for astronomy. And what they discovered was a faint signal that they could not account for in all directions of the sky, independent of the time of day or the season of the year. It's really a lot of fun to read the accounts of how they eliminated one false possibility after another, including having to clean out the pigeon crap that had accumulated in the horn and that they were worried was interfering with their signal. They discovered the Big Bang. Serendipity or sweat? Which brings me back in my final minutes to Jansky. Was Jansky's discovery serendipity or was it sweat? He was given a task by his boss to find out what radio signals there were that might affect transatlantic communications. And he did. He found thunderstorms and he found this signal from the Milky Way. It took him over a year of data taking before he could understand what he got. Took all the hard work of maintaining this device and building it and so on. Was it serendipity or was it just sweat? I think in a lot of cases you can't separate it. And I am not proposing a solution to any of these. I think a few things are clearly sweat, but Jocelyn Bell Burnell worked like very hard to build that array, but it was her keen eye for the anomaly that allowed the discovery of pulsars to be made. Oh, this is a great story. Jodrell Bank had just finished an all-sky survey at 400 megahertz with their big 250-foot telescope. And the minute that they heard about the pulsar discovery at this rival institution, Cambridge, they went back through their chart recordings because they had passed over pulsars. Why didn't they detect them? And sure enough, there was on the chart recording over one of the pulsars, blip, 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 unmistakable blips. And someone had circled it and written interference. So serendipity, sweat, the keen eye in the right place. Let me end with Mort Roberts, one of the discoverers of dark matter, and a quotation he made at an International Astronomical Union symposium. I think that they'd only been having these for 20 or 25 years. And he says, the period dating from the first IAU symposium has been exciting and productive. The continued development of new instrumentation for both space and ground-based observations promises an even more fruitful period ahead. But it's more than instrumentation that is needed. Democritus, over 2 millennia ago, eloquently described another vital ingredient. Who seeks will find the good only with labor and pains. The bad, however, is found by everybody without seeking. Thanks very much.
Well, that was terrific. Thank you so much. Do we have some questions?
Guess I'm wondering about Jansky. In the 1930s, when he discovered the emission from the center of the Milky Way, I mean, was the structure of the galaxy really understood by then?
Ah, that's a great question. And in fact, you know, they knew at the time that the center of the galaxy was likely in Sagittarius. And that came for looking at the distribution of globular clusters. And globular clusters tend to concentrate there. But it was very uncertain. And what's really interesting is that there's no way Jansky could have seen the galactic center. For one thing, his telescope didn't point far enough south. But for another thing, at that frequency, radio waves don't penetrate all the way to the galactic center. So what he saw was the general increase of more or less everything as you go in towards the center of the galaxy. So he, well, that was the interesting thing about the discovery of hydrogen. Within a few years of the discovery of hydrogen, Oort had mapped the galactic plane and the IAU moved the galactic center. That was what really determined the galactic center. You can see part of the hydrogen coming toward you and the other part going away, and there's a line of symmetry.
I mean, you can tell that the Milky Way becomes wider just visually when you're looking at that. But I was wondering how much was actually known at the time. And it seems like the radio discoveries really played into the understanding of the fact that there is a galactic center. We're not at it. It's someplace else.
Oh, yeah. Yeah. But I think that was pretty well understood by that time, in part because people understood about interstellar dust.
When you say move, did you mean move positionally or distance from? Because back in, I'm talking many years now, I had seen various figures of the center distance of the center of the Milky Way, 30,000 years, 30,000 light years, 27,000 light years, so forth and so on, as the technology got better and better. I also assumed that maybe they were doing the age-old thing of just rounding up. If it was really 27, they were just rounding to 30. You know what I'm saying?
Yeah. Oh, yeah, yeah. Well, there's two questions, and one is where on the sky is the galactic center, and the second question is how far away it is.
Mm-hmm.
And that second question was my first IAU meeting was in New Delhi, and there was a group convened to change the distance of the galactic center. and they changed it from 8.2 to 10 kiloparsecs, and they got it wrong. And now we, as you point out, we have very sophisticated techniques, and it's very well known to maybe 5% or something like this. But it's difficult, you know, distance is always a problem. Distance is always a problem.
I have a question from YouTube. It says, can you briefly elaborate as to why the signal curve on the frequency time graph must originate from a great distance?
Ah, yes. Okay. Yeah, that's it. So, yes, I guess I didn't explain this. On the horizontal x-axis is time, and the vertical axis is frequency. And so you see it first comes in at the high frequency, and then later the pulse comes in at lower frequencies. A very characteristic shape. As a radio wave passes through the interstellar medium, if it interacts with electrons, then it is retarded. And the amount it's retarded depends on the frequency in a very precise way. So when you see a chirp with this particular curved shape, you know it's passed through some interstellar matter. Now, from the shape and the amount of delay at one frequency compared to another, you can calculate how much matter it had to pass through. And that was the truly stunning thing about the Lorimer burst, was that it couldn't come from within the Milky Way. There wasn't enough gas. It had to come from very far away. And we now know the whole field of fast radio bursts is really blossomed just in the last few years. And we now know some of them are coming from very far away, too, from galaxies that are very far away. And 1,000 of these things impinges on the Earth every day, but they're just a millisecond wide. And if you're looking over here and it comes there, it's gone. You know, you got to be looking at the right spot at the right time within a millisecond or two. And so telescopes have been built specifically to track these things and are now discovering hundreds and thousands of them. Very mysterious. We still don't understand their origin.
I have a comment more than a question. That was a terrific talk, by the way. I enjoyed it very much.
Thank you.
So there's a lot of philosophical undertones in the title of your talk, obviously. So when you look into astronomy, which is essentially an area of discovery, serendipity has to play a role all the time, meaning somebody being at the right time, at the right place, in the right circumstances, right, to see something. So you could always see that anybody that works very hard and puts a lot of sweat will need some serendipity for discovery. The question, of course, is you can have a lot of sweat without serendipity, in which there will not be any discovery.
Well, there are some, I think Rieber is pure sweat. You know, he went out to find something and he finally found it. It wasn't where he was looking for, but what he found was exactly what he was looking for. He was looking for Jansky's radiation. He was trying to understand what that was. The Lorimer burst, Dunk was looking for bursts. He was looking for dead pulsars that only come to life now and then and give off a burst. But what he found was something very, very, very different. So that's, I think, the fast radio bursts are serendipity. I think Jansky's work is, I don't know about Jansky's work. Rieber's work is certainly not. Following up a known phenomena, getting more information on it. I mean, this is tremendously valuable. But you know, when his name eludes me, right? There was a Nobel Prize given for measuring the shape of the black body curve from the Big Bang to incredible accuracy. That was done on a satellite that was built and designed just for that. So a lot of hard work.
Any serendipity in your own career?
You know, I never thought about that until this evening when I was preparing for this. So that's why I said, thank you very much. I did an experiment once for the heck of it, just to see, how should I put this? I got time on the 140-foot radio telescope to see if I could find a hole in Milky Way's hydrogen, just because I was told there wasn't one. And I thought, they can't know that. They can't know that. There's got to be. I mean, there might be. I mean, and it turns out for technical reasons, scattered light and everything else like this, it's not so easy to find that with a normal telescope. And I found a kind of hole, more or less. And I was just doing it for the heck of it. Okay, end of story. Well, it turned out that that was valuable to a lot of people. Knowing that place with the least hydrogen in the sky was valuable to a lot of people, because at wavelengths that hydrogen absorb, that limits your ability to look deep. So my discovery was not serendipitous, but the use of it was.
Comment on YouTube from Rocky. It says, luck is the meeting of preparation and opportunity.
Yeah. Mm-hmm.
You might have covered this in your talk, and unfortunately I might have missed it, but I'll ask it again anyway. When you keep on mentioning hydrogen, are you talking about the actual hydrogen from the Big Bang, hydrogen heliums formed from stars, or you're talking about neutral hydrogen at the 21 centimeter line?
Yeah, it's neutral hydrogen that was created during the Big Bang, but it right now is atomic and cool and seen through the 21 centimeter line. Yeah.
Thank you.
Sure.
So what particle is responsible for serendipity?
Yes. I'm sure some of you have remember the Larry Niven Ringworld book, where some aliens have been interfering with reproduction on Earth and breeding people for luck. They get lottery winners to marry each other and so on.
That's Ringworld.
Yeah.
So another question from YouTube. Does luck or serendipity diminish accomplishment? Does it make it stand at a lesser level than discovery based on reasoned insight?
Boy, very interesting question. Certainly those who have not made great discoveries might sneer at a mere accident. I would just like to point out, though, that the Nobel Prize is awarded for the discovery, not for the cleverness of the discoverer, which is why a lot of very smart scientists have not got the Nobel Prize, and a lot of people that were in the right place at the right time and recognized what they had.
Or knew the right people, right?
I think that's the key word, recognize what you had, because you showed us that graph that someone circled as interference.
Right.
They made the discovery, but the serendipity was there. I guess the other part didn't match up.
Yes, and this is an interesting thing, because I knew a guy who was here, early astronomer at Green Bank, and he was trying to do very accurate calibration with a horn, and found a little excess antenna temperature, a little excess radiation that he couldn't account for. And once people found the radiation from the Big Bang, once Penzias and Wilson published that, there were a half a dozen. Well, that Project Echo that I showed. Where is that slide? 40-meter balloon. This thing. They built the horn reflector antenna here to work with Project Echo. And when the project was done, there was a engineer named Ohm, of all things, OHM, who wrote up the final report for Bell Labs Technical Journal. And he added up all of the noise from the expected from the receiver, expected from the antenna, expected from this, compared it to what was measured. And there was an excess of noise. And he said, well, I guess everybody just lowballed the sensitivity of their equipment. He had discovered the microwave background.
That's a common theme, though, throughout history.
Yeah, I guess so. And you could argue that Penzias and Wilson certainly didn't know what they had, but they knew they had something. And in fact, it was it was a group at one guy, Ken Turner, who knew what was happening at Princeton with the theory of the Big Bang, and said to Penzias and Wilson, hey, you better talk to these theoreticians. And that's when they understood what they happened. So in their paper, they say a possible explanation for the observed excess noise is the one given by Dickey Peoples-Walsh in a companion letter in this issue. So they just bumped the whole idea of what it was to the Princeton group that's been, we're starting to actually search for it.
So now that's a big bone of contention that Penzias and Wilson won the Nobel Prize, but Dickey and his coworkers who seemed to actually understand where it was coming from didn't.
It's given to the discovery, not the discoverer.
But yeah, at some level, you have to understand what it is. So, I mean, going way back, Galileo observed Neptune. Just purely by chance, they get passed by either Jupiter or Saturn, and it was in some of his pictures. He had it drawn in there as a star.
Yeah, interesting.
Didn't know what it was. Or the guys who circled the pulsar as interference.
Right. Yeah.
But they didn't know what it was.
We had a GBT telescope operator here who unfortunately now is deceased, but he was quite the amateur astronomer and astrophotographer. And one evening when I was working and he was working, he showed me an image of what looked like a comet, a fuzzy blob that he tracked for a couple of days. And he said he sent the information to Cambridge, the Harvard Planetary Science Center, and they said they couldn't fit an orbit to it. And so they didn't know what to do with it. And it was almost certainly now one of these interstellar interlopers that, you know, they didn't know how to do it. You know, it wasn't followed up. And let me just say also, as I was preparing for this, I was thinking, you guys are operating in a high serendipity environment. You really are. You're paying attention to what you see. You're probably looking at a part of the sky that nobody else is looking at that night. And there's just, you could write books about the discoveries by amateur astronomers of things that are of great interest. So.
Yeah, on that, the image that Lou showed of the asteroid going through IC 443, it was totally accidental. He was imaging IC 443, and then he calls me up late at night, goes, what the hell is this thing going through the field? And we're going through it and saying, oh, it looks like an asteroid, and then contacted another friend of mine who was able to figure out which one it was. We were hoping it was something undiscovered, but...
And what's so great about that image is that if you just averaged them all together, you wouldn't have seen it.
That's what happened. When I stacked the data, the rejection algorithm kicked out the outliers. I would have never known it was there, except that I had some crazy gradients I couldn't figure out when I was processing. So I went back through the raw data, and I have a processing program that allowed me to blink through all the images really quick. And as I'm blinking through, there it is. You see it move. Wow.
That's great.
There was another, during that same period, there was actually a tiny little, I guess, meteorite. Looks like it was really small that crossed through the atmosphere. Now, Jeremy thinks it's a cosmic ray. I disagree. I think it's a meteorite because the way it changes color, but pretty cool. I mean, that's also, I mean, we're on the topic of serendipity. So
yeah,
catching something like that. I could do that stuff all day. Just the problem is it's too cloudy.
You do radio astronomy.
I could get into radio astronomy.
That allows you to have a life.
Yeah. I guess you can do it during the day.
Another question from YouTube. In modern radio astronomy, particularly at Green Bank, what is the field size that can be observed at any one time? Or is this able to be adjusted for a particular observation?
Yeah, very interesting. Our pixels are several wavelengths across, actually something like 24 wavelengths across. So if you're dealing with 21 centimeters as the wavelength, then your pixel is like, a meter, several meters. And it's just hard to get many of those together. So our field of view, most of the receivers that we use are single pixel, one pixel. To make a map, you scan back and forth. Now we have exceptions where we have small ones. I mean, at higher frequencies, the equipment, remember what Rieber's single pixel looked like? It was a big can. And at higher frequencies, your pixels can now be a few millimeters in size, a few centimeters in size, and we can pack them together. But we're on the verge of a technological breakthrough that will allow us to really expand the number of pixels. But for the Green Bank telescope, the field of view is relatively small. And it changes with frequencies. Green Bank telescope observes over 3 orders of magnitude in wavelength. So it really is quite different from the lower frequencies all the way up into the millimeter.
So all those images that you see, it's just 1 pixel and you're just rastering across like that?
Yeah, we have a few, we have a 16 pixel and an 8 pixel system. Oh, and one, actually at 3 millimeters, we've got a 225 pixel system. It doesn't do spectroscopy, it does continuum work, picks up dust. So, but this is something that we are very much involved in the instrumental development of, is multi-pixel receivers. Yeah, that's why the fast radio bursts stayed hidden for so long. We're just looking at a tiny patch of the sky at any one time.
At Green Bank, how successful are you in keeping the interference at a low level, or is it getting more difficult?
It's always getting more difficult. All of those constellations of satellites are transmitting in the radio. And so we're looking at tens of thousands. Collision avoidance radar. That's going to be a problem.
5 gigahertz band, right?
It's this, yeah, we hide in Green Bank, and it's a lot better than most any place, but it's always a problem.
So it's not really the on the ground stuff, the microwaves and the cell phones. It's more.
Well, we've kept cell
space.
phones. We've kept cell phones from working here. There are no towers around. But the thing about the satellites is they're unregulated, basically, and they're looking right down at us. Yeah. Nice little lighthouses in the sky.
Is there any way you can get an algorithm to filter all that out without destroying any of the useful data?
Yeah, we're working on that. Yes. Yeah. In the most brute force sense, we put a filter in the receiver that just does not allow those frequencies in. But it's going to be a game of dodging from now on. And, you know, my worry is, what if one of those things malfunctions and just starts broadcasting up and down the spectrum? How do you retrieve a malfunctioning satellite? You don't. Who's responsible? No one really.
Buy a powerful shotgun, I don't know.
The only good news is that they're interfering with each other. And so we may see some standards coming into effect that will help. Well, listen, if you have other questions, let me not drag this on any longer, but if you have other questions, shoot me an email. I'd be happy to answer the ones I can or point you to a better reference. As I said, this has really been delightful, and I've learned a bunch. I hardly knew anything about the Jupiter radio burst beforehand, although I know the people involved. And I was, well, that's another story. There's so many stories in our field. It makes it interesting.
Thanks for great presentation, man. Thanks.
Thank you very much for spending your evening with us. It was really wonderful.
Thanks so much. And I hope to see you. Hey, when you come to Green Bank, give me a call, stop by. I'll give you an insider's tour.
Sure. That'd be great.
Happy to do that. Just tell them over in the Science Center to give me a call. And if I'm around and able, I'd be happy to do that. After all, it's your taxes that are paying my salary.
Thank you very much.
Okay. Bye-bye.
Bye-bye. Thank you.
Bye-bye. Thanks.
Actually, a really interesting question just came in on YouTube about pattern recognition being an important skill for radio astronomers. Said, are many of the astronomers also musicians?
Where's my banjo?
I'm thinking Brian May, right?
I actually am in a band, and I play the banjo and the fiddle. And it used to be that the early visitors to Green Bank, and I'm talking now here in the 1960s, would always bring their instruments with them. And you could always more or less pull together a string quartet. So, I don't know in general, but a lot of astronomers play music, that's for sure. And I'm one of them. So,
yes, especially if you don't have cell phones, right? You got to find something to do.
Oh yeah, it's like living the 1990s life, right? How is it possible?
Go get your banjo, and Jan can open up her guitar, and you
Hey, yeah, what kind of guitar is that? I've noticed that back there.
It's just an acoustic folk guitar from long, long ago.
Oh, what? There's no reason to apologize for an acoustic guitar. Okay, bye now.
Bye-bye.
Thank you very much. Take care.
Thank you.
Thank you.
Thank you. Bye.
Okay, well, thank you, Jeremy. That was fascinating.
Yeah, it was a good talk.
Yeah.
Really good speaker.
Yeah.
Great presentation.
Yeah.
Are you going to say goodbye to the YouTubers, or how does that work?
We're going to shut it down. So you want to close the official meeting, and then we'll...
Goodbye, YouTube.
Okay, well, thanks everyone. We had a great turnout, great questions. Thanks everyone for participating on Zoom and YouTube. And we hope you'll find us next month. Jeremy, I don't think you gave a preview of next month. Would you want to do that?
We're expecting to have Michelle Thaler. We've tried to get her in the past, but she's pretty busy with the web launch. So hopefully her schedule will start to open up now, and we'll have her next month.
I can't wait for that. She's
You
like
mean that's not certain yet, Jeremy?
I hope it will be. She's doing her best to protect the date, so we'll try to keep her in there. I'm actually waiting for her abstract, so we should get that fairly soon.
So anyone in the club who'd like to stay on, you can ask questions of the new astrophotography expert crew.